Okay, hello and welcome back to the weekly live lectures on mechanics and control of robotic manipulators. I am Isaac John, the TA for this live tutorial session. So we have reached the end of this course. We have completed all 8 weeks worth of lecture, on the topic of mechanics and control of robotic manipulators. So until week 6, we were dealing with various topics in robot mechanics, which essentially comprises of mechanics and dynamics. Kinematics and dynamics. And in the final 2 weeks, we were mostly focusing on various motion controllers of robotic manipulators, which can be broadly classified as open loop or closed loop. And within those classification, we have seen the cases of kinematic and dynamic motion control systems. So for this week, this is basically an extension of what we have seen in the previous week. It's an extension of control systems. We are yet to discuss about this one another control system called cascaded control. So we'll basically go through a summary of cascaded control for the remainder of this lecture, for this session. And various other topics for week 8 was simulation of various dynamic control systems in MATLAB. And then using the principles that we have studied over the previous weeks, we also there was also a demonstration of how to model a mobile robot using the learned DH approach. So for this lecture, we'll be mostly focusing on cascaded control and some sample problems that you can expect for during this week's worth lecture. All right, so let's see what the cascaded control is about. So you can basically implement cascaded control for a system of this form. We call this as an input-affine form. So like for any general system, if you can write a system of equation of this form, x1 dot as f1 x1 plus g1 of x1 x2, then x2 dot would be f2 x1 comma x2 plus g2 x1 comma x2 x3, then x3 dot would be so on and so forth, and then finally xn would be fn x1 all the way to xn plus gn as a function of x1 all the way to xn multiplied by a control vector. So essentially, all these equations represent a first order ordinary differential equation. And the coefficient of this term g would basically depict the control input to control, to regulate or to stabilize each and every system. But the term over here in the place of a control input is essentially a state variable of the succeeding subsystem. And here also like x3, the variable that is in place of this control term x3 is again is a state variable of the succeeding system actually. So those sort of systems or the systems that we can represent in those form, we call them as input affine forms. So if you take the case of our robotic system, we can also express our robotic system in an input affine form. Basically, the first equation, or depicted in equation 2, this is the well-known equation. The kinematic mapping between task space to joint space. So the vector over here, labeled as mu dot, is the velocities in task space. In task space. This task space. And over here would be the velocities in joint space. And we basically know, the Jacobian matrix, that is based on the kinematic architecture of the robot that basically maps the velocities in task space and joint space. And we also have seen, how to model the dynamic equations of motion or the governing equations of motion of a robotic manipulator. That takes off a general form as tau would be, the torque of acting on the generalized coordinates would be a mass matrix m of q multiplied by the acceleration q double dot plus, the vector of Coriolis and centrifugal effects. And if you rearrange this equation, to obtain these accelerations, simply by rearranging that, you will get q double dot would be tau minus n of q dot. The whole term would be pre-multiplied by the mass matrix m of q inverse. So this is what I've written over here, in equation number 3. The first equation is the kinematics in pure kinematics. One second. Yes. I'm doing this regularly, actually. I have a class to do. Okay. I'm not a PhD, I'm not a BTech student, I'm a PhD student. PhD, yes. Uh, you have a class also? No one told me not to. I'm in the middle of a class. Okay, so where were we? Yeah, so the first equation number 2, basically depicts the velocities in joint space, and the second equation also depicts the acceleration, from the dynamic equations of motion. So how can you relate that with the general input affine form? So if I substitute in place of mu dot, if you do a direct comparison between these two subsystems with, the general input affine form, you can say that the variable x1 would be the task space velocity, task space position variables mu, and then x2 would be or I think I may have I probably may have mixed the coordinate systems. I'll just keep this as q double dot instead of mu double dot. So here x1 would be mu and x2 is q dot, right? And then comparing the equation 1a with equation 2, the term f1 of x1 is basically 0, and g1 of x1 would be the Jacobian matrix J of q. And comparing the second equation 1b with this dynamic equations of motion, f2 of x1 comma x2, this would essentially be m of q, negative m of q inverse n of q dot, and g2 multiplied by x1 comma x2, this would be m of q inverse, and the control input u would be the vector tau, the actuation torque that you would be supplying into the motors. So you can essentially represent the robotic system into this input affine form. So once we have done this, once we have essentially obtained this input affine form, like what we have seen in the earlier week, we want the errors of the system to asymptotically tend to 0, right? So basically, we have two first order systems, and we want the two first order system to behave as per the error dynamics, represented in equations 4a and 4b. So again, these are first order ordinary differential equation. So the general solution, or you can call the homogeneous solution, would look something like this. E1 would be an arbitrary constant C1 multiplied by e raised to minus k1t, and E2 of t would also look like an arbitrary constant C2 multiplied by e raised to minus k2t. Right? This is what we want our system to behave, because the response of the system would be like this. Right? So what can you infer from this? As time tend to infinity, this error term E1 would tend to 0. And for the second subsystem, again here as time tend to infinity, the error of the second system E2 would also tend to 0. So this is how we want the system to behave, and we are trying to force the system to behave as per this error dynamics. So now let's see what these terms x1, what this term E1 is. E1 is nothing but the difference between the desired state x1 desired minus the actual state x1, right? So if you go back to the previous slide, x1 is nothing but mu. So x1 desired is nothing but mu desired, and x1 would be mu actual, right? For example, if we want our robot to follow a desired position, through a trajectory, this would be coming from a trajectory, and this mu actual would be coming from the sensors. The actual position that the robot is currently on, right? So E1 is nothing but the error difference between the first state variable, x1 desired and x1. When it comes to a robotic system, that becomes mu desired minus mu actual. And if I substitute in place of E1, if I substitute this equation, x1 desired minus x dot, this equation would become something like this, right? x1 desired minus x1 dot plus k1 E1 would be 0, right? So now in place of this x1 dot, I'll be substituting the first equation. X1 dot is f1 of x1 plus g1 of x1 multiplied by x2. This is the first state equation. It's basically the robot kinematics. So in place of x1 dot, I will be substituting this equation, and we'll be ending with this equation, right? X1 desired dot is over here. This equation is over here, and then this k1 E1 will be over here, right? So now, if you go back for the first system, the control input is this term x2, right? So in order for us to make the system follow this first order error dynamics, what should be the control input x2? So from this equation, you have to find x2. If you try to solve for x2 from this equation, you will get an equation like this. It's just a simple manipulation of this equation, right? So if I bring this term over to the other side of this equation, and I pre-multiply everything with this g1 x1 inverse, you will get the following solution: x1 desired dot plus k1 E1 minus f1 of x1, the whole term pre-multiplied by g1 of x1 inverse. This would give you the control input x2. Right? So if this is your control input, right? If x2 is your control input, and if you substitute this value of x2 into this first equation or into this first subsystem, your system will behave as per this first order error dynamics, right? So that as time tend to infinity, your the errors would asymptotically tend to 0. Right? So this should be the control input for the first subsystem. But then there is a problem. Let's see what this statement says. The term here x2, this should be the control input for the first subsystem in equation 1a, and to achieve the desired error dynamics in 4a. So this is equation 4a. We have to substitute this control input into the first subsystem so that we can get this error dynamics. But x2 is also a state vector for the second subsystem as well, right? if you go back and see, x2 is also a state vector for the second subsystem. So we cannot really control, or we cannot really have a control input like this, because it's also a state vector. It varies as per, it depends upon how the system is basically behaving. We cannot directly control this input, because it's also a state vector. So what can we do? This is what we desire for our x2 to behave, but we cannot really force it, because it's also a state vector. So what can you do? So what we propose is that, like, x2 dot or x2, I'll write it over here. This x2 is also a state vector. State vector of subsystem 2. Let's write the subsystem 2 over here. The governing equation would be something like x2 dot would be f2 multiplied by x1 comma x2 plus g2 multiplied by x1 comma x2 multiplied by u. Right? So what we can do is, in order to make the first subsystem behave according to the first error dynamics, we will, from now onwards, we'll just call this equation, equation 7, as x2d, right? And then what we do is, we use the control input of the second subsystem u, so that x2 would, the state vector x2 would tend to x2 desired as time goes to infinity, right? So if we use this control input x2, this control input u of the second subsystem, so that we try and force the state vector x2 into this x2 desired, this one, x2 desired, then we can guarantee that the first subsystem E1 dot plus K1 E1 would asymptotically converge to 0. So how do we do that? So now we'll be referring to this term, the desired control input for the first subsystem as x2 desired, and we'll see how we can make use of the control input u, so that x2 would tend to x2 desired. All right, so now let's look into the second subsystem. So this is the second subsystem. I label this as equation. Maybe I'll just keep it as such. This has already been discussed. Now, if you consider the second subsystem, we want the second subsystem to follow the second order error dynamics, E2 dot plus K2 E2 should be, this should be equal to 0, where K2 should be greater than 0. Because the response of this error dynamics would be E2 of t would be like an arbitrary constant, C2 e raised to K2 t e raised to minus K2 t. And this error term, second error, E2 would tend to 0 as time tend to infinity. And now we also know that this E2 is nothing but the difference between the desired state vector x2 desired and the actual state vector, where now the desired state vector x2 desired is the control input for the first subsystem, and this x2 would be the actual state, the actual measured state measured by the sensors. If you go back 2 slides before, we know what this x2 is. X2 is nothing but q dot, the velocities. Okay, so now just like what we did with the previous equation, we'll just replace this. We'll just replace E2, E2 dot with x2 desired dot minus x2. So if I label probably maybe this as, what is the equation number? If I label this as equation 8, I'll replace E2 dot with x2 desired dot minus x2. So you will end up with x2 desired dot minus x2 dot plus k2 E2 would be equal to 0. And we also know what this x2 dot is. From the second subsystem, x2 dot is f2 x1 x2 plus g2 x1 x2 multiplied by u. So x2 desired dot minus, instead of this x2 dot, I'll substitute this equation minus f2 multiplied by x1 comma x2 minus g2 multiplied by x1 comma x2 multiplied by u plus k2 e2 would be 0. So here we have to find an expression for the control input u. So now u would be x2 desired dot minus f2 x1 comma x2 plus k2 e2, the whole term pre-multiplied by g2 x1 comma x2 inverse. This will be u. I'll just make a box around this. So if this would be your control input u, your system will behave as per this second order error dynamic, right? Where as time tend to infinity, this error would tend to 0. That basically means the x2 would try to, converge to x2 desired, right? So you can force x2 to converge to x2 desired. And if that happens, if x2 converts to x2 desired, your first order error dynamics will also be satisfied. So that's why we call this as cascaded control, right? By trying to force the second system, by trying to force the second state vector into this x2 desired, we basically achieve this the first order error dynamics for the first system. So that's how it gets cascaded. Now, that's not all. One more thing that we have to ensure is we should also ensure that this control law or this design is stable. We have to ensure the stability of this control input. Even if we apply some control input, we should guarantee that the error will stay within a bound. It should not grow. It should not grow unbounded. So we basically use a technique, in nonlinear systems or in nonlinear control system. It's called this Lyapunov direct method. Lyapunov direct method for assessing the stability of the system. So I'll just briefly explain the procedure. How can we use this Lyapunov method to assess the stability of a system? So the first step to assess the stability of the system is, we have to come up with a candidate function. Maybe, find a candidate function. It can be anything, but there are certain rules in which you have to, you have to follow while selecting a candidate function. So we'll assume that the candidate function v of E1 comma E2, the function of errors of the first system and second system is something like half of E1 transpose E1 plus E2 transpose E2. Maybe you can consider this to be something equivalent to, energy, maybe like if you have a mechanical system and the kinetic energy is basically proportional to the square of velocities, right? X1 dot square and if you have two variables, it will be like x1 dot square plus x2 dot square. So similarly, you can consider this candidate function as some form of an energy or something equivalent to an energy. And then again, this is not an exclusive choice of a candidate function. You can choose any other candidate function provided they follow some conditions, right? So the conditions are, to obtain these candidate functions, if we are able to find a candidate function v of e1 comma e2, we have already come up with a candidate function, but this is not an exclusive choice. We can have any other candidate function, but the condition for choice is such that v of e1 comma e2 should be greater than 0 everywhere except at the origin, right? So if we can come up with a candidate function which is positive, as in basically any positive definite function would basically do, but it has to be positive everywhere except at the origin. So how would this function would look like? So if you try to plot this function, E1 transpose plus E2 transpose in 3 dimensions, on the vertical axis, you can have the candidate function V, and on the other 2 axes, maybe if I plot this axis to be V1 and this axis to be V2, it would look something like a concave function, something like this, right? In 3D, it would look like a bowl shaped function. And this point would be the origin, E1 comma E2 equal to 0 comma 0. So as you can see, if you move away from this origin, the term V would be basically positive. If you go in any direction, the value of V of E1 comma E2 is basically positive. So that should be one of the conditions. It should be positive everywhere except at the origin, where it can be 0. So what it basically says is that this is like a concave function. So the derivative of this function, if you take the derivative of this function, v dot of e1 comma e2 with respect to time, it would be like, if you take the derivative of this function, it would be like e1 transpose e1 dot plus e2 transpose e2 dot. This should be less than or equal to 0. Right? So the first condition is, you have to find a function that is positive everywhere except at the origin, and the derivative of that function should be less than 0 everywhere except at the origin. So as you can see, you can see that, if you drop a ball or if you drop an object here, they would always, the point of stability would always be at the origin. Even if you drop something over here, due to this negative gradient or due to this negative slope, it would always tend to come to this origin. So if you can find a candidate function, something like this as a function of this this error variables E1 and E2, so that it's positive everywhere except at the origin. And if you can also guarantee that the derivative of that function is negative everywhere except at the origin, then you can basically say that the system is stable. For any values of E1 and E2, the system is basically stable. Or in other words, the errors are always going to be are always going to be bound. But the converse is always not true, because even if you are not able to come up with a function, you know, even if you are not able to come up with a function that satisfies these 2 conditions, that doesn't mean that the system is not stable. It's just because you probably need further more analysis, or you may need further more checks to prove that the system is stable or unstable. But for the time being, if you are able to come up with a positive definite function, as a function of this error variables, and if you can prove that the derivative of that candidate function is 0 everywhere except at the origin, if you can prove that, that basically means that your system is stable, because your error bounds, wherever how much ever error you have, maybe at some finite error values, maybe somewhere around here, E1 comma E2, due to this decreasing slope or due to this decreasive derivative, the errors, as time evolves, the errors would always come to this zero, to this zero origin. Right. So now let's see what these. Let's see if you go with this equation. Let's see whether the errors are the errors for this cascaded system will follow this whether those this equation is indeed less than zero or not. We'll try and see that. So we know this error E1 is nothing but x1 desired minus x1. Right? So if you take the derivative, E1 dot would be x1 desired dot minus x1 dot. So we know what this x1 dot is. This is nothing but x1 desired dot minus f1 of x1 plus g1 of x1 multiplied by x2. Sorry, multiplied by x2. But we also know x2 is nothing but E2 minus x2 desired. Sorry, I think it's the other way around. X2 desired minus E2. X2 desired minus E2. So if I substitute this equation, x2, here, let's see what we get. E1 dot, this would be x1 desired dot minus f1 of x1 plus g1 of x1. This whole thing multiplied by x2 desired minus E2. X2 desired minus E2. So I'll just open a curly bracket over here. And x2 desired, we have already obtained this expression for x2 desired. It's this one actually. G1 inverse K1 E1 plus x1 desired dot minus f1 x1. So if I substitute that, I'll get G1 of x1 inverse. Then what were the remaining terms? K1 E1 plus x1 desired dot minus f1 x1. Then one more term would be there. That will be E2. So I'll just close this bracket and I'll close the square bracket as well. Right? Where, this entire term is x2 desired, and this entire term inside that red bracket would be E2, sorry, x2. All right. So now how to go from there? So if I simplify this equation, simplifying everything out, E1 dot would look something like, we have an x1 desired over here, x1 desired dot over here. And this G1 x1 and G1 x1 inverse, would get cancelled out. And there is also an x1 desired dot over here. And with this minus, these two terms will get cancelled. And then we have an f of x1 here. And inside also we have an f of x1 that will also get cancelled. So the remaining terms are, I believe, the remaining terms are probably, this term minus K1 E1, this term over here. Then, this term, this G1 X1 and this term. That will be like minus, or is it plus? We have a minus over here and minus over here, so that becomes a plus. So plus G1 of X1 multiplied by E2. So we got the expression for E1 dot over here. Expression for E1 dot we got over here. And if we try to substitute that into this derivative term of the Lyapunov equation, V1 dot is E1 transpose E1 dot plus E2 transpose E2 dot. So if I substitute this E1 dot into this equation, what will I get? So V of V dot of E1 comma E2, this will be E1 transpose E1 dot plus E2 transpose E2 dot. So we'll get something like E1 transpose multiplied by minus K1 E1 plus G1 of X1 E2. So if I expand this out, plus we also have this term as well, E2 transpose E2 dot plus E2 transpose E2 dot. So if I expand this out, V dot E1 comma E2, this would look something like minus E1 transpose K1 E1 plus E1 transpose G1 of X1 E2. Then we also have plus E2 transpose E2 dot. Now this is the updated equation of V dot. Now one more step is we have to find out the expression for this E2 dot. This also we have to find out, and then we have to substitute this E2 dot into this equation. So our ultimate aim is we have to check whether this equation, V dot is less than 0 everywhere. That is the condition for stability. So once we find out this equation for E2 dot, and once we substitute that into this equation, if it is clear that it's going to be 0, it's going to be less than 0 everywhere, that means that the system is basically stable. So now let's find out an expression for E2 dot, where E2 dot is nothing but X2 desired dot minus X2. So I'll write it like this, X2 desired dot minus, this X2 dot we already know from the state equation. This would be F2 X1 comma X2 plus G1 X1 comma X2 multiplied by U. Okay, so now our task, this would be essentially, this is going to be your E2 dot. Now, what you have to do is you have to find the U, you have to find the control vector U, so that this E2 dot, once you substitute this E2 dot into this expression, this whole V dot would be less than 0. So how can you do that? So you already have a term over here, this is actually a negative term. So even if E1 is negative, if E1 is negative, this E1 and E1 would square it, that becomes positive, but the negative sign over here would make this entire term negative, right? So even if E1 is positive or negative, this whole term is always going to be negative because of this negative sign. We have a positive term over here. So that can be either positive or negative, depending on the values E1 or E2 takes. And we also have this term, E2 transpose E2 dot. So what we are trying to do is, this term we are a bit unsure. It can be positive or it can be negative. So if E1 and E2 are both positive or both negative, this term will be positive. If one is positive and one is negative, this term will be negative. If both are negative, this will be also positive. So what we want to do is we have to find the control input U, so that if you substitute this E2 dot into this equation, this entire term will also be negative, just like the first term, right? So what I propose is, if we can somehow make E2 dot, somehow we want to make this equation into this form. I'll just write a note over here. If maybe, yeah, if E2 dot is, how would it look like? If E2 dot is minus K2 E2 minus G1 of X1 comma E2, right? So suppose, or if E2 is of this expression, if I substitute this E2 dot into the V dot equation, what will happen? So V dot of E1 comma E2 would be something like minus E1 transpose K1 E1 plus E1 transpose G1 of X1 E2 plus E2 transpose. In place of this E2 dot, I'll substitute this equation. This is just an assumption. If E2 dot is this one, so now it'll be like minus K2 E2 minus G1 of X1 E2. So if I simplify this out, you will get it as V dot of E1 comma E2. This would be like minus E1 transpose K1 E1 plus E1 transpose G1 of X1 E2 minus E2 transpose K2 E2 plus, or we have a minus actually, minus E2 transpose G1 of X1 E2. G1, or this should be E1 actually. Suppose this is E1. E1, so this will also be E1. And this will be E1. So if you now take a look, this term over here and this term over here will get cancelled because both are the same term. Now your V dot E1 comma E2, this will become minus E1 transpose K1 E1 minus E2 transpose K2 E2. So this term is always going to be less than 0, irrespective of whether, irrespective of whether E1, E2 is positive or negative or a combination of positive and negative, doesn't matter. This V dot is always going to be less than 0. So that essentially means the system is going to be stable. The stability of the system can be ensured. So if E2 dot is something like this, we can basically guarantee that the system is stable. So now if you go back to the previous earlier equation, if we can choose a control input U in a way that E2 dot would be this expression, we can pretty much guarantee that the system is stable. Now you have to find out what U is going to be, so that E2 dot is this expression. So like if I substitute this term over here, maybe if I substitute this term over here, and you can solve for U, how would U look like? So maybe I'll just write it over here. Well, maybe I'll label this as equation A, and if I label this as equation B, I'll also write a note over here. We want, I think, choose the control input U so that E2 dot would be minus K2 E2 minus G1 of X1 multiplied by E1. So this would imply V dot of E1 comma E2 would be less than or equal to 0. So now solving for the control input U, solving for the control input U, I'll just solve it for the control input. Now what will it look like? E2 dot is nothing but minus K2 E2 minus G1 of X1 comma multiplied by E1. This would be X2 desired dot minus F2 plus G1 multiplied by U. All right. So how would it look like? So minus K2 E2 minus G1 of X1 E1 minus X2 desired dot plus F2 the whole multiplied by G1 inverse. This would be your control input Q, right? Or if I write it a bit more neatly, the control input U would be G1 of X1 inverse uh, have I made any mistakes? Yeah, the big minus sign should be somewhere around here. So yeah, everything becomes positive. The signs have to be flipped now. This would be a positive sign. This would also be positive. This would be positive, but this F2 would be negative. Right. So your control input U is nothing but this is G2 actually. So G2 of X1 comma X2 inverse minus F2 X1 comma X2 plus X2 desired dot plus K2 E2 plus G1 of X1 multiplied by E1. This is how your control input should look like, for the system to be asymptotically stable. Now, if you compare this equation, or if you compare these variables with our actual robotic system, we basically know that, F1 of X1 is 0, G1 of X1 is this Jacobian matrix. F2 would be minus M inverse N, G2 would be M inverse Q, and X1 is mu, X2 is Q dot, and U would be your control input dot. So you can substitute all those variables into this equation so that the final expression for the control torque, you will be able to obtain that final equation. So that's about this kind of cascaded control. You would use the control input for the first subsystem so that, control input for the second subsystem so that the first subsystem can also be asymptotically stable. So it goes from a kinematic loop then into a dynamic loop actually. So yeah, that's why it's called a cascaded loop. But there are two layers into it. First, ensure the stability of the first subsystem, decide what control input first subsystem needs, and use the second subsystem to supply that control input. So yeah, that's about cascaded systems, cascaded control. Now we'll solve some sample questions for week 8. Again, this is like a continuation of what we have learned over the previous week, because I believe the assignment questions are mostly from control, motion control of robotic manipulators, which is an extension of what we have covered from the previous week. So let's see some questions. So first question is about inverse dynamics. So this it's a true or false question. It says Inverse dynamics control would still track a desired trajectory even if the following conditions are not satisfied. So there are three conditions. Q1 desired double dot is not zero. Q desired dot equals Q dot desired of zero, and Q desired of zero is Q of zero. So does this make any sense? Does it uh, you know does it feel like it's true or false?
False.
Okay, I got an answer that this is false. Can you tell me the reason why? Why is it?
Because the given three conditions are the control laws for the inverse dynamics. They have
Exactly.
asked whether it is, even if the following conditions are not satisfied, the inverse dynamics would follow. So the option would be false.
Option would be false. Yes. For inverse dynamics to work, these conditions will have to be satisfied. Otherwise, it will not work. So like I'll just briefly say why that is so. So we know the dynamic equation of motion of a robotic manipulator is something like this. Tau would be m of q double dot, plus n of q dot. So this inverse dynamics control is an open loop control, right? Inverse dynamics control is basically an open loop control law. So basically, with control, what we do is we want the robot to track our desired trajectory. So suppose, for example, if you have a desired trajectory that the robot should follow or the robot arm should follow, you can consider this to be a trajectory, that we want our robot to follow. So the trajectory is specified by the position as a function of time, velocity as a function of time, and acceleration as a function of time. These are the desired positions, desired velocities, and desired acceleration. So what you do for this open loop control is you would simply plug these trajectory variables, position, velocity, and acceleration into this dynamic equation of motion. And then from here, you will be obtaining this control vector torque. So whatever you are obtaining from this control vector or this control input, you supply into the robot manipulator. So in order for this open loop control to work, I have already said that there is a desired position, something like this. Suppose that your actual start position is somewhere here, this is your actual start position. I'll just denote it as Q of 0. And actual start velocities would also be Q dot of 0. And this point in green color, this is the start position of the desired trajectory, Q desired of 0 and Q desired dot of 0. If the actual start position is different, from the start position of the initial trajectory, your robot would still, execute a similar trajectory, something like this. Both of them are similar, the desired and actual are similar, but you can see that there is always going to be a finite offset, between the desired and the actual trajectory, right? So in order for this to not happen, the initial position of the initial positions and velocities of the desired trajectory should coincide with the initial positions and velocities of the actual trajectory. These 2 points should coincide. So that is what condition 2 and 3 basically says, right? Initial positions and velocities of the of the desired and actual positions and velocities should coincide. Otherwise, there's always going to be this finite offset. And the first statement essentially says Q desired double dot should not be 0, right? The acceleration of the desired trajectory should not be 0, because otherwise, if it is 0, this term would be 0. So your torque estimated would be different, right? So in order for this term to not be zero, Q desired double dot should also not be zero. That basically is defined by condition. So that's why in order for this inverse dynamics to work, these three conditions are to be followed. Okay, so the answer is indeed false. Now, moving on to question 2. Again, it's a true or false question. It says motion-based or model-free control methods are easy to use, but sluggish and produce poor tracking performance. So we have seen two models. We have one called motion-based. We call them as model-free. And another scheme of control would be model-based. One example we have over here is this PID control. And for the model-based control, we have, this, whatever we have seen earlier, this inverse dynamics control. Then we have, in the lectures, we have seen this something called computed torque control. So the question says model-free controls, these controls, something like PID control, that does not rely on any information about the mathematical model of the robot. PID control methods are easy to use, but sluggish and produce poor tracking performance. So is it true that can we apply the statement for PID controllers? It essentially says controllers like PID control are easy to use, but they are sluggish and produce poor tracking performance.
It's
Would
true,
that
sir.
be? It's true. Yes. Okay, thanks for answering. The reason is PID controllers you basically you have a proportional gain multiplied by the error, then you have a derivative gain multiplied by the rate of change of error, then you have an integral gain multiplied by the multiplied with the integral of the error. So here you can consider this to be a control input torque. So here you can see that there is no information about the model of the robotic system, right? Because a model can be depicted by this dynamic equation of motion, m of q multiplied by q double dot plus n of q multiplied by q dot. Then if there are other terms, you can model that as well. So if you take a look at this PID control law, there is no information regarding the model, no information regarding the physical properties of the system. So the main disadvantage of this is that it will be sluggish, because from this inertia matrix, from this mass matrix, consider that if you have a two-dimensional robot, right, a robot that has 2 degrees of freedom, it has more inertia in 1 degree or in along one coordinate, and it has less inertia in the other coordinate. So that physical property will be captured by this mass matrix, right? So if you can incorporate this mass matrix into the control law, if the robot has to move in a direction with more inertia, the control input will be high. The control input will be scaled by this mass matrix, right? So the control input would be very fast. Because of the information that this mass matrix has, the control action can be very fast because it already has that information. And suppose if the robot has to move along a direction with lower inertia, it only needs to provide a lower control input, lower force. So since all the information are already available with this mass matrix, it can easily, it can be very fast. But in these sort of control laws, model-free control laws, it does not have any information about the model. So it will only do this corrective action once the error grows. So it has to wait until the error grows, in order for it to do a corrective action, right? So if a robot is putting equal effort to move along the direction with more inertia and less inertia, it will probably move very slowly in the direction having more inertia, right? So because of low torque, it has to wait until the error to grow so that more torque can be applied. So it has to wait for some time in order to do some corrective action. So in that regard, this model-free controls are sluggish, but they are also easy to use, right? Here, you only have to measure these errors, from the desired trajectory and the actual coordinate from the sensors. You only have to measure this error. You don't really have to model the system. Sometimes it will be very difficult, right? If the system is very complex, writing the dynamic model is going to be a bit difficult. But this PID control, it can be implemented on any system, almost all systems that we use on a day-to-day basis, they have some form of PID control. So in that regard, they are easy to use, but they are always a bit sluggish, to respond.
Sir, I
So
have a doubt.
yeah,
So you told model based will have inverse dynamics and computer torque control. Will also
yeah,
that computer velocity control and inverse kinematics will also fall under this?
yeah, true, because they also have some information about the physical model of the system, right? Because if you consider the inverse differential kinematics, inverse differential kinematics, that control law basically says your mu desired should be J of Q multiplied by Q desired dot, mu desired dot. So here, you have the information about the robots, robots motion in the form of this Jacobian matrix. When the Jacobian matrix is probably close to a singularity, in order for your robot to achieve a specific velocity, since it is nearer to the singularity, your Q desired dot will be also very high. This Q desired dot would be considered as your input. So depending upon the nature of this Jacobian matrix, your control input would also be immediately scaled up. Or rather, this Q desired dot, this would be your control input to your motors. This would be J of Q inverse mu desired dot. So, depending upon the actual structure of your robotic manipulator, this J of Q inverse would be scaling, that would be scaling this mu desired dot. So, Q desired dot can be appropriately selected. I hope that is clear in that regard.
Yes,
So,
sir. So
yeah.
next, is inverse differential kinematics and inverse dynamics the same, or they are both a different?
No, in inverse kinematics, we are only dealing with the velocities. We are not really dealing with the dynamics of motion. So in one example, what you can say is that if your robot is actually moving very slowly, the inertial effects very slowly, such that you can basically ignore the effects due to inertia, effects due to the moving inertia. This basically would give you a fairly good performance. But if your robot consists of very large, heavy bodies that are moving in a very fast, moving very fast, then this would probably not give you a very good performance. You may have to go with inverse dynamics. But then inverse dynamics will also have its own problem. In the previous question we have seen, it has to follow these conditions. And the robot should also be free from external disturbances as well. So if all those things are not matching, inverse dynamics would also not be good. So then you have to go for this computer torque control, which would also take care of all the other disturbances and issues due to non-conver. If the robot is starting from a different start position rather than start position of the desired trajectory, you can actually use this computing computer torque control. So like each robot has its own benefits. Each controller has its own benefits, but then uh, you cannot interchangeably use everything for different applications. These control laws are developed based on several assumptions. So if that assumptions are not honored, or if they are not satisfied, then most likely those control laws would probably not work. When those assumptions we chose while deriving these control laws is not honored, or if they are not satisfied, then the performance is not going to be as we expect. Okay.
Okay, sir.
Okay, thank you. So now we'll move on to the next question. Question 3. So now that we have discussed in brief about the motion controls that we have seen, can you identify this question? Can you answer this question? Identify the closed loop control laws from the following. So we have 6 control laws, out of which some of them are open loop, some of them are closed loop. Can anyone identify which of them are closed loop? Which among them are closed loop control laws?
Computed velocity is closed loop.
Okay, computed velocity, this is
Computed
closed loop.
torque, cascaded,
This is
and also
closed loop.
PID.
PID is closed loop. Okay, cascaded is also closed loop. Then you have this inverse dynamics over here. Then you have inverse differential kinematics over here.
They both
These,
are open loop.
yeah, they both are open loops. Yes, I agree with that. So I believe there is no need for any sort of clarification for that. If any clarification is required, please let me know. But the answer is, 4 among those 6 options are closed loop. Only these 2 are, open loop. So if there is any doubt regarding, any of these control laws, let me know. I can go back and explain. Now, moving on to question 4. From the following choices, select the case that correspond to motion-based model-free control with gravity compensation. So, which among the following basically is something that is model-free control? What about the first option?
It will not come. First option won't come.
First option won't come. What about second option?
Was the mathematical model.
Yeah, that also has a mass matrix over here, right? So you have to model it mathematically to get this mass matrix. That is also looks to be false. What about the third equation?
Third one is the correct option, I guess, because it has only proportional derivative
Yeah,
and the gravity compensation term.
the gravity term. What about the fourth one? That doesn't look to be right because it has a mass
Mass
term over
matrix.
here. Fifth term, this does not look to be even correct, right? Kp multiplied by q desired plus q. That does not look like an error term. That is false. Sixth term is also not correct because again it has a mass matrix over here. So here it seems like the only correct option is like, there's a proportional term and a derivative term and just a gravity vector. So in that regard, option 3 seems to be the only right answer. Option 3. Right? Because it question clearly asks it should be a model-free control, purely based on motion. Right? So the term inside this bracket is nothing but the error. Q desired minus Q is the error between the desired position and the actual position. And Q desired dot minus Q dot is the error in velocities. All right, so option 3 seems to be the correct answer for this question. Moving on to fifth question. For a land-based wheel mobile robot and water surface vehicles, the degree of freedom is. So like at the tail end of this week's lecture, we discussed something about mobile robots, how to model the kinematics and dynamics of mobile robots using the principles that we have learned earlier, using the DH models and the Newton-Euler methods, how to model the kinematics and dynamics. So this is a very generic question based on mobile robots. So here it says about land-based wheeled mobile robots and water surface vehicles. So how many degrees of freedom does that robot have?
3, sir.
It's actually indeed 3. That is correct. So can you identify what are those 3 degrees of freedom? How many variables do you need to identify the position of a wheeled robot?
And move along Y, rotate about XY plane.
Exactly, correct. So if you consider this to be the body of a mobile robot and this to be the maybe left wheel and this to be the right wheel, the mobile robot can basically go in X direction, it can go in the Y direction. It can position itself anywhere along this coordinate X coordinate. It can also position anywhere along the Y coordinate. It can also orient in any arbitrary configuration it wants, like a rotation about the plane. I'll probably denote it as phi. So like you need 3 variables, X, Y, and phi to fully define the configuration of a mobile robot, of a wheeled mobile robot and water surface vehicles, right? Because water surface vehicles, they only operate on the water surface. It won't go underneath. So what happens if it goes underneath? Underwater vehicles will have 6 degrees of freedom, right? It can move in 3 dimensions, X, Y, Z, and it can also rotate about 3 axes. So like underwater robots have 6 degrees of freedom. Aerial robots will also have 6 degrees of freedom. But wheeled mobile robots, those who operate on the ground, and water surface vehicles, those who operate on the water surface, they only have just 3 degrees of freedom. So that is indeed correct. Option 3 is indeed correct. Moving on to question 6. The expression for proportional integral control with a feed-forward term it's just a PI control. So what about the first option? Here like the velocity itself is the feed-forward control. That term does not have any feedback variables in it. So whatever that is free from feedback, that term you can consider it to be a feed-forward term. So the first equation, you have a q desired dot, then kp multiplied by q desired minus q, then ki multiplied by q desired minus q, the integral of the error. So this equation looks to be correct, right? You have a proportional term and you have an integral term, and then you have a feed-forward term over here, q desired dot. So option 1 looks to be correct. Option 2, it does not look to be correct because even though it has a proportional and an integral control, the feed forward term over here is QD because these do not dimensionally match, right? This is a velocity term, but this is a positional term. The dimensions of these 2 terms are not matching, so that is not correct. Third option, again, the dimensions are not matching. This is Kp multiplied by Q desired dot minus Q. Instead of position Q desired, you have Q desired dot over here. So that is also not correct. Option 4, again, due to this dimensionality issue, this is also not correct. Question 5, we have a negative term over here, Q desired. Again, that is also not dimensionally consistent. That is false. Question 6 is also false because, instead of adding the integral term, they are subtracting the integral term over here. So here, the only correct answer seems to be option 1. Proportional integral control with feed-forward term. Earlier, like we have seen proportional integral control with the gravity compensation term. Both are similar in some ways, but basically different. So option A, is the correct answer. We move on to the question 7. It's like a yes or no question. You have to select it either if it is yes or if it is no. So the question says the input affine form used for cascaded control scheme is given as equations 1 and we have seen this in the beginning of this lecture. X1 dot is f1 of x1 plus g1 of x1 multiplied by x2, and x2 dot is f2 x1 x2 plus g2 x1 x2 multiplied by u. So the desired error dynamics, we want these two systems to follow these two error dynamics. E1 dot plus K1 E1 is 0, where E1 is x1 desired minus x1. And for the second subsystem, we want the second subsystem to follow this error dynamics, which is E1 dot plus K2 E2 is 0, where E2 is x2 desired minus x2. So the statement is, from the perspective of a robotic system, can the state vector x2 be used as a control vector for equation 1 to achieve the error dynamics as per equation 3? Can we really use x2 as a control vector? So that, as a control vector for equation 1, to achieve the error dynamics as per equation 3. So what it does is, E1 dot plus K1 E1 is 0. We know that E1 dot is x1 desired dot minus x1 dot. So if I substitute x1 dot from equation 1, you will get, and if you substitute that into this equation, you will get x1 desired dot minus x1 dot plus K1 E1. This would be like x1 desired dot minus f1 x1 minus g1 x1 x2 plus K1 E1. So the question says, can you use this x2 as a control vector? So now x2 would be x1 desired dot plus K1 E1 minus f1 x1, the whole pre-multiplied by g1 x1 inverse. So essentially, if you substitute this x2 into this equation 1, this subsystem will follow this error dynamic, E1 dot plus K1 E1. The question says, can we really do that? Can we really treat this x2 as a control vector? Is it possible? Is it yes or is it no? Just like we have seen in the computer torque control. So, well, the answer is it's actually no, because if x2 is like this, if x2 is as per this expression, and if you substitute this x2 into equation 1, you will get this equation. This is what we desire. But the problem is we cannot really, treat this as a control input. We cannot really control it because x2 is also a state vector for the second subsystem. Right? So what we do is we basically use this u vector so that x2 will go to this expression. And once we do that, x1 will follow this error dynamic. So in that regard, we cannot really read this x2 as a control vector. We have to make use of, or we have to get the help from the second subsystem as well. From the control input Q. So that's what the question basically says. The answer should be no. We cannot. It says, can the state vector be used as a control vector for equation? The answer is actually no. It cannot be used. It has to be controlled by the U vector of the second subsystem. We cannot independently, treat x2 as a control input. Okay, this is actually from the cascaded control we have discussed at the beginning of this session. Answer is indeed no. Yeah, the description says, since the state of a robotic system are coupled, the state vector of the second subsystem cannot be used as a control vector for the first subsystem. We cannot independently choose this control input x2, because this is the state vector of the second subsystem. They are coupled in a way. Okay, so that's about question 7. So yeah, now we'll be using, this will be the final question actually. As per our class notation, the computer torque control law can be given as, which of the following expression, is the computer torque control out of the 6 options? Any answers? So the basic principle of computer torque control is like we have a robot, we have a model of a robot on our hand. From the dynamic model, we can have this expression tau is a mass matrix sum of q multiplied by q double dot plus n of q dot. So the purpose of the computer torque control is we want the system to behave as per the second order aerodynamics. E1 double dot plus K1 E1 dot plus K2 E2. We want the system to behave as per this second order aerodynamics. The reason is because the system, the general solution for this second order ordinary differential equation would look something like this. E1 of t would be C1 e raised to minus S1t plus C2 e raised to, plus S1t plus S2t. Right? Where this S1 and S2 are nothing but minus K1 plus or minus root of K1 square minus 4 K2 multiplied by 2. So if your gains K1 and K2 are positive, the terms S1 and S2, the quadratic, the roots of this quadratic equation S1 and S2 are going to be negative. And as a result, the response of that second order system is going to be will asymptotically tend to 0 as time tend to infinity. So that is why we want our system to behave as per this second order error dynamics. So in order for the second order error dynamics, in order for the system to follow this second order error dynamics, what should be the control input torque? So instead of this E1 double dot, if I substitute in place of E1 double dot, I'm going to substitute x1 desired double dot minus, sorry, it's not x1. It will be e double dot is the derivative of acceleration. So I'll substitute in place q desired double dot minus q double dot, right? And for the expression of this q double dot, I'll obtain the expression of this q double dot from the actual model of the robot, actual dynamic model of the robot. So from dynamics, q double dot is nothing but tau minus n of q dot, the whole quantity pre-multiplied by m of q inverse. So if I substitute this expression for q double dot into this, into this expression, I'll get q1 desired double dot minus m of q inverse tau minus n of q dot plus k1 e1 dot plus k2 e2. This should be 0. And from here, I can find out the control input. So that will be q1 desired double dot plus k1 e1 plus k2 e2. This whole term multiplied by a mass matrix m of q plus this vector of Coriolis and centrifugal effects. This will be our control input. And this is also essentially the computer torque component. Right? So we derive this from our requirement that we want the system to follow the second order dynamics, so that as time tend to infinity, the errors in positions and errors in velocities will asymptotically tend to 0. So in order for the system to achieve the second order dynamics, our control torque should be, as per this expression. And from the options, I can see probably which of the options makes sense. I think this option, the final option, I guess, right? Oh, I've already given the correct answer here itself. So it looks like option, the final answer option looks to be the correct option. So I hope we can all agree on that. There is also one more term, right? G of Q. Here, I have considered the model without G of Q because I didn't choose to model that. But maybe you can also have a gravity term here as well, G of Q. And if you have other effects in your own robotic system, like damping due to friction, damping due to viscous friction or Coulomb friction, maybe some effects due to backlash, all these things can also be modeled, if you can model. And it would also get reflected, in the control law. But I believe the correct answer for this question, as per our class notation, the computer torque control can be computed as per this equation. I think everything else looks incorrect. So the answer is indeed the final option. All right. So with that, we'll wind up today's session. And this will be the end of the weekly tutorial session. We have covered all 8 weeks of live discussions on various topics on mechanics and control of robotic manipulators. So I hope the course has been useful for all of you. Because I believe the lectures itself are quite sufficient, for you to solve the weekly quizzes, and also more importantly to understand, the fundamentals. If there are any questions, I'll be happy to take it now. Otherwise, we shall wrap up the session.
Sir, the control of computed velocity control is when t tends to infinity, the q tilde becomes 0. Is that correct, sir?
Yes. So for computed velocity, we have the kinematic equation, something like this. From kinematics, we have mu dot would be j of q multiplied by q dot. And for computed velocity, our objective would be as time tend to infinity, the positions, the error in position, maybe E of t, which is nothing but the difference between the desired position and the actual position. This should tend to 0. And in order to make this happen, we want the system to behave as per this first order aerodynamics. E1 dot plus K1 E1. This should be 0. So, the general solution or the homogeneous solution for this first order differential equation would look something like this. E1 of t would be C1 e raised to minus K1t. Right? So as time tend to infinity, this error would tend to 0 as per this response. So for the computed velocity control, we want the system to follow this first order aerodynamics, and then we'll get that similar to what we did before. For dynamics, we can also do the same thing here as well, and then we'll be able to get an expression for this q dot. So I hope that is clear.
Yes, sir.
Yeah.
So we have a question in the 8th assignment, the longitudinal direction equation of land-based mobile robot, which I can't find in the lectures covered by Shantakumar sir. So where should I find this, or where should I learn this?
Okay. I thought he was. I don't know this entire equations, but basically, you will be deriving the entire dynamics of a mobile robot, right? That will also have a similar equation, something like this. Tau would be m of q multiplied by q double dot plus n of q dot. I believe he's deriving something of this form in one of the lectures. So where this tau vector would now look something like fx, fy, mz. And this mass matrix would be a 3x3 mass matrix. And this q double dot would be x double dot, y double dot, and then a rotational angular acceleration, r double dot, then one more vector you have over here. So for a mobile robot, the coordinate system is fixed like this. If you have a mobile robot, if you consider this to be the wheels, you can consider this to be the left side, this to be the right side, this to be the front, this to be the back. And the coordinate systems are almost always assigned like this. On the robot, we assign the coordinate system like this. Along towards the front side, you will have this x-axis, and along the left and right side, you have the y-axis. So, this direction, of left to right direction, you can call this as lateral. And front to back direction, you can call this to be longitudinal. So, I believe you asked for the forces, right? The forces acting along the longitudinal direction. So if you multiply this two metrics, if you multiply this equation on the right-hand side, the entry correspond longitudinal. If it is longitudinal, the terms corresponding to the first element, first entry, Fx, that would correspond to the forces acting along the longitudinal direction. And the term corresponding to Fy would be the forces acting along the lateral direction. And the third entry would be the torque, along the vertical z-axis. So if you can find out this expression from his lectures, what you get from the first row would correspond to the forces acting on the longitudinal direction. Because Fx is basically the longitudinal force, Fy is basically the lateral force, and Mz would be the torque, above the z-axis.
Okay, sir.
Okay. Thank you. Any further questions?
So could you solve a problem that involves the calculation of DH parameters? I still don't have any clarification
Okay.
regarding that.
Inverse kinematics of what? Which one?
No, sir. DH parameter calculation, that is alpha I, that calculation. Week 4
Okay.
or 5 months.
You want to solve a sample problem?
Yes, sir.
Let me see if I have the slides, if I still have the slides. Which week did we discuss on that? Week 4 or week 3?
Week
Maybe
4 or 5, sir. 1 minute, sir. I'll also check.
week 3, I guess. I think.
It's
Or
in
week.
week 3 and it is also in week 4 also.
Okay, let me check.
Week 3, sir.
Week 3. Okay. I'm not sure if I have the slides available with me. Week 5, I have. Yeah, this looks to be one of the. This looks to be week 3. Yeah. So, what problem would you like to solve? We have an RP robot over here. We have what other problems do we have? We have one question over here, question 3.
I
Or
think this one is okay, sir. The previous one that you showed.
okay. Let me see if there are. Uh, okay. What about this one then? This problem for the given diagram, find the DH parameters of the second joint. Do you want to solve this or the previous problems?
Okay, sir. This one is okay.
Now we'll
Because it
solve
has
this.
3.
Okay. So this robot apparently this robot has how can I say this? It looks like this robot has 3 joints, right? So I'll try to make a schematic of this robot, just for better understanding. So it has a first, it has a joint going vertically upward, something like this. So that it can rotate about the vertical axis, something like this. Then it has. Let me try and complete this. Then it has another link which has a join perpendicular to the plane of the board. That is It's coming like this, and it has a different link. And here it has, sorry, I think I'm completely making a mistake. So it has another joint, something like this. And one more final joint, something like this. So this robot has 3 joints, as per the direction of this z-axis. If you consider this link, this shaded link over here, you can consider this link to be fixed to the ground. And inside that, you have one link, maybe shaded in this. I'll use some colors probably. Maybe this yellow colored link, you can consider it to be the first link going inside. And maybe this green colored link, you can consider it to be the second link. And this blue colored link, you can consider it to be the third link. So the first step for DH method, what you have to do is, the first process is, I'll just write it over here. First step is to find out z-axis for all joints. So basically, as per the DH convention, the z-axis of all the joints should lie along the axis of the joint. So in this case of this robot, all the joints are vertically pointing upward, right? So the z-axis should also be along the vertical. So according to this depiction, you have a robot with 3 joints. The direction of the first joint is vertically upward along this axis. And the direction of the second joint is also vertically upward, along this axis. And the third joint is also along this axis. So what you can do is you can fix the first Z1 axis anywhere along this length. You can fix the Z1 axis anywhere along the line of rotation or along the axis of rotation. So maybe for the time being, I'll just keep it here itself. So I'll denote this axis over here as Z1 corresponding to the first revolute joint. And I'll keep the second Z axis along this line, maybe somewhere around here. I'll keep it like this. This will be my Z2. And my third axis, I'll keep it. You can actually keep it anywhere along this length. It's not a problem. So I'll keep it, just to be consistent with our problem, I'll just keep it over here. I'll keep it over here. So this will be my Z3. You can also choose the direction to be anywhere as per your question. Just to be consistent with the question, I choose Z3 to be here, but there's no harm in choosing the direction of Z3 being like that. So the question asks, find the DH parameters of the second joint. So what you have to do basically is you have to find out the DH parameters for this Z2 so that you can relate Z1 to Z2 using DH parameters. Or you can relate frame 1 to frame 2 just by using 4 DH parameters. So the first step is find out the Z-axis of all the joints. Now the second step would be to find out the x-axis. Like once we have identified all the z-axes, second step would be to identify the x-axis. So the procedure to find out x-axis, xi would be along the common perpendicular of zi and zi plus 1. Right? So in order for you to fix the x-axis, it should be along the common normal of uh, zi and zi plus 1. So let's consider this fact. If you want to find out the direction of x1, you have to look at the direction of z1 and z2, and x1 should be along the common perpendicular to both of these axes, x1 and x2. Right? So this is the axis of x1, z1. This is the axis of z2. So the common perpendicular to be either this or a direction that is perpendicular to the plane of the ball. But just to be consistent with the notation of this textbook, we'll choose x1 to be, along this direction. This will be my x1. And if you want to fix the direction of x2, it should be along the common perpendicular to z2 and z3. So the common perpendicular would be along this direction. That will be x2. And for the final joint, it can be along any direction as per your preference. So just to be consistent with the question, I'll choose x3 to be in this direction. But in reality, it can be any direction of your choice. It can come out of plane as well. So now using DS parameters, how can you relate frame x1 to frame 1 to frame 2? So as you know, there are 4 DS parameters. So the first DS parameter, I'll try to fit everything over here. Maybe I'll just move this figure a bit. Somewhere, okay. I try to move this figure slightly to the right. Yeah, there are 4 DS parameters. The first DS parameter is alpha I. This is nothing but the relative orientation between zi plus 1 and zi along xi. So if you consider the second frame, what is the relative orientation between z2 and z1 along x1? Alpha I basically takes care of that relative orientation. So if you take a look at this z1 and z2, what is the relative orientation between z1 and z2? They are always parallel, right?
Parallel.
Yeah. So maybe even at a different orientation of the robot, like this is only at a specific orientation, right? Only at this configuration. Maybe if you consider the robot to be at a different configuration, maybe if you consider this joint to be rotated, if you rotate this joint, what will it look like? X2 will be now out of plane. X2 will look something like this. Maybe at a different configuration, x2 would it will go out of plane, x2 dash, but z2 would still remain the same, right? At any configuration, z2 is always going to be vertically up, because this link is will only rotate about Z2. So at any arbitrary configuration, Z2 is still going to be the same, but X2 will keep on rotating about this circle, about a vertical circle with the center along Z2 axis. So the first DS parameter alpha I, that is the relative orientation between Zi plus 1 and Zi. So in this case, relative orientation between Z1 and Z2 is 0. So in that regard, alpha 1 is going to be 0. And now the second DS parameter. Now second DS parameter would be AI. Sorry, this is alpha I minus 1. Second would be AI minus 1. This AI minus 1 would be the relative position between Zi plus 1 and, sorry, these are actually Zi minus 1 and Zi. So AI minus 1 would be the relative position between Zi minus 1 and Zi along Xi, right? Earlier it was relative orientation, now it's relative position. So relative position between Zi minus 1 and Zi along Xi. So now what is the relative position between Z1 and Z2 along X1? That is the question.
It's A1.
That will be A1. Yeah, if you have a link length, length of this yellow portion, if you consider that to be A1, AI minus 1 would now be A1. AI minus 1, this will be A1. Now the third DS parameter would be theta I. Now this is where we have a significant amount of change. Theta I would be the relative orientation between xi minus 1 and xi along zi. Right? Now you have to identify the relative orientation between x1 and x2 along z2. What will that be? Relative orientation between x1 and x2. So if you consider this joint to be a revolute joint, the revolute joint will be parameterized by a joint variable theta 2 probably, right? So maybe at one configuration, if x1 and x2 are parallel, theta I would be 0, right? If both of them are parallel, theta I would be 0. But since this is a revolute joint, x2 can be anywhere, x2 can be oriented anywhere parameterized by the joint variable theta 2, right? Because x2 can be anywhere within this circle. This circle, you can consider it to be, out of plane. So x2 at any configuration, it can be like this. 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 Since this is a revolute joint, it can always be at any configuration. So that relative position relative orientation between x2 and x1 will be characterized by the joint variable that is theta 2. And now the final DS parameter, that will be di. This would be the relative position between xi minus 1 and xi along zi. Now it should be the relative position, relative position between xi minus 1, which is x1, and x2 along z2. So relative position between x1 and x2 along z2. What will that be?
D2, sir.
That will be d2. Yes. So di will now be d2. Di will be d2. So irrespective of the orientation, if it is oriented like this, if it is oriented like this, if it is oriented like this distance, the perpendicular distance along x1 is always going to be d2. It won't change. The only parameter that is changing depending on the configuration of the robot is the joint variable, that is theta 2. So yeah, that's how we assign, base parameters. So the first step is you have to first identify the z-axis which lies parallel to the joints, be it a revolute joint, be it a prismatic joint. Then you assign the x-axis. Once you do that, once you assign the z and x-axis, now you try to find out the ds parameters, alpha I, ai, theta I, and di. And they have to be in that specific sequential order. Alpha first, then ai second, theta I third, then di would come as the final parameter.
Okay,
So yeah,
sir.
that's how you assign frames and find out these parameters.
Sir, next we have another joint, right, sir? This is revolute joint. The other joint is prismatic joint.
Yes.
What
You
is
have a
that, sir?
prismatic joint.
So how will that joint work, sir?
So revolute joint, you can only rotate two links about the axis of the revolute joint, but prismatic joint, it'll help you. A prismatic joint, two links will slide, along the axis of the prismatic joint. So let me try and find an example where we have prismatic joints. Yeah, in this example over here. So here you have basically two links. Sorry. Yeah, you have two links. I'll just depict that sequentially. So if I consider this to be the ground, this entire thing to be ground, you have one link like this. Sorry. You have the first link, something like a block, and this will be attached to the ground. This can also be considered to be the part of ground. And you maybe I'll denote the rotating link with the color. This will be the first link. And I'll attach the first link to the ground using a revolute joint. So the axis of the revolute joint will be perpendicular to the board. So this will be your, sorry, perpendicular to the board. You have your Z1 axis, right? So that this link can rotate like this, vertically. And now the second link is basically the second link is now connected to the first link using a prismatic joint. So I'll just try to depict the second link, something like this. So I'll just use a different color. So yeah, this would be the second link. So basically this second link now can slide back and forth. It can slide all the way inside, or it can go all the way outside. So the motion of the second link is like back and forth sliding, because it's like a piston cylinder movement, actually, back and forth motion. So since this is a prismatic joint and the motion is along this direction, your z-axis you can fix your z-axis anywhere along this You can fix it anywhere along this axis of the prismatic joint. Maybe I'll fix it somewhere around here, So this will be my Z axis. This will be Z2. So I hope that is clear. So maybe if you want to find out the DS parameters, you have your first joint, something like this. Maybe I'll draw it in a different configuration, for more clarity. Instead of this tilted configuration, I'll just draw in a horizontal configuration, something like this. This is the first link, and you have the second link going inside, and this is the first join. So I'll have Z1 coming out like this, out of plane, and Z2 would be along this axis. So I'll just depict Z2 like this. This will be Z2. Now that we have fixed Z1 and Z2, what we have to fix the x-axis. So as I have said, for the x-axis should be along the common normal to Z1 and Z2. So Z1 is out of plane, Z2 is horizontal. So common normal to Z1 and Z2 is vertically upward direction. So I'll depict this to be x1. Right? That will be my x1. And x2, I can fix it anywhere, because since it's the final joint, I can now make x2 like this. This will be my x2. So I'll just erase this off. Now, how do you find out the DS parameters for this one? Now you have the first transformation. These are individual transformations. Alpha I minus 1 would be the perpendicular, that'll be the relative orientation between, what is it, Z1. I'll just denote it as with the correct index as well. So alpha 1 would be the relative orientation between Z, alpha 2 now actually. Or is it alpha 1? Or I'll just rather keep the thing as such. Alpha I minus 1 would be the relative orientation between xi minus 1 and xi, or I think it's z actually. Zi minus 1 and zi along xi minus 1. Right? So the relative orientation between Z1 and Z2 along X1, what is that? X1 is vertically up. So if I rotate minus 90 degrees, if I rotate minus 90 degrees about X1, Z1 will be now in this direction, right? Z1 and Z2 will be aligned, right? I hope it's still clear. So
Yes,
if alpha I minus 1, or if alpha 1 is minus 90 degrees, now once you do the transformation, x1 would still be the same, but z1 now will become something like this. New z1. So I'll denote it as z1 dash. x1 would still remain the same because we are rotating about x1 only. And the other joint, z2 would be like this, z2 would be like this, and x2 would be vertically up. This will be x2. Now the second transformation would be ai minus 1. ai minus 1 would be a relative position between zi minus 1 and zi sorry, have I got it wrong? Yeah, relative position between zi minus 1 and zi along
xi
xi minus 1. Yes, that is correct. So what is that be? What is that going to be?
d2, sir.
Is it is it d2? Because z1 is here. Z1 is in this axis. Z2 is also in this axis. Relative position along xi minus 1. So x1 is along this direction, right? So, there is no offset between Z1 and Z2, right? Because along X1, right? Because they are lying on the same line.
0.
Yeah, so that is 0 actually. So, AI minus 1 in this instance would be 0. I hope that is clear.
Sir, yes, sir.
Okay, now another thing would be theta I. This would be relative orientation between xi minus 1 and xi along zi. So now you have to find out the relative orientation between xi minus 1 and xi, sorry, x1 and x2 along z2. So x1 is pointing vertically upward, x2 is pointing vertically upward. And since this is a prismatic joint at all configurations, they are always going to be parallel. There is not going to be any relative orientation between them. They are always going to be parallel. Maybe at a different tilted orientation, something like this. X1 would be like this at a tilted orientation, and X2 will be like this. Z2 would be, like this, and Z1 dash, Z1 dash, since we have done this alpha I1 transformation, this ZI1 dash will be something like this. This is Z1 dash. All right. So theta I, this is at a tilted orientation. This is at a non-tilted orientation. Theta I would be relative orientation between xi minus 1 and xi. So in this case, relative orientation between x1 and x2 along z2. What is the relative orientation? They are basically parallel, right? So theta I in this case is going to be 0 for a prismatic joint. It's always parallel. Now the final joint parameter di, this will be relative position between zi minus 1 and sorry.
It's not 0, no, sir. It's theta 1.
It's not theta 1 because x1 and x2 are always parallel. How can it be theta 1? We are only considering the DS parameters for joint 2, just for joint 2. We are not considering DS parameters for joint.
Okay.
Right? If you're trying to relate the zeroth frame to the first frame, then theta 1 will come. But now in this case, we are only trying to find out the DS parameters for frame 2, between 1 and 2. Yeah, prismatic, yes. So the relative position between xi minus 1 and xi along zi. This will be your di. So this will be x1, this will be x2. The relative position between x1 and x2 along z2, that will be d2. This is a variable, right? Because it's a prismatic joint, it's a variable. It varies with respect to time and configuration. So the final transformation di or d2, which basically accounts for the perpendicular distance between x1 and x2 along z2, would be the final ds parameter, that is d2. Okay, I hope that is clear enough.
Yes, sir.
Okay. Okay, so let's wind up with that. We have, I hope we have covered almost all topics on mechanics and control of robotic manipulators.
Sir, external same like this only, sir. Internal
Yeah.
assignments.
The patterns will be very much similar, but there will be more number of questions, but quizzes, the final exam will be similar. The level of questions will be very similar to the weekly quizzes.
Is it possible to share this remaining also, sir? Earlier you uploaded only up to 3 weeks, I think, record.
No, I have uploaded everything actually. Up to week 6 or 7, it should be available. I think it's there. The YouTube videos the recorded sessions are available, and the presentations are also available.
Okay, sir. Up to 6, sir.
No, up to previous week it should be available. Up to week 7 it should be available. The slides and the recorded presentations are available. Okay. So with that, I shall wind up this session, the final session on this course. Thanks for joining, and all the best for the exam.
Thank you, sir. Thank you.
Thank you.
So we'll have only 50 questions, right? Or more than 50 we'll have?
I think 50 questions. I'm not entirely sure, but I think it should be 50 questions.
Okay. Will we be provided any formula sheets like thing? Because last time I had an exam formula sheet where they didn't inform at all. So I was sitting preparing for the formulas for a long time.
Last time for which course?
It was renewable energy, sir. It is a
It
12-week
depends.
course.
It probably depends on the courses, right? So I don't think we'll be providing any
This course
formula sheet.
you won't provide, right?
This course?
Yeah, this course it won't be provided, right?
I believe so. I don't know how the exams are going to be conducted, but probably not. Are you asking about the marks, the final marks?
No, not about the marks. Whether see, I had last exam. They provided the formula itself.
I don't think we'll be providing any formula books, or
But they
it
didn't
won't be.
inform also. So I wasted my time
Oh,
learning those formulas. So that's why I had
okay.
a doubt whether here.
Yeah. No, I guess it won't be provided. But I don't think there are plenty of formulas. Maybe
Yeah,
there
we
could be
don't have.
formulas. I think there are formulas in maybe the Newton-Euler dynamics. There could be some formulas. But yeah, I suppose it should not be too difficult, I hope.
Okay,
Because
sir.
we were able to solve tutorial problems without you know intensive use of formulas. I thought it would be more conceptual rather than anything formula based. So it should not be too bad. I suppose. I hope. Should be fine.
Okay, sir. Thank you, sir.
Okay. Thank you. All right.
Yes,
Okay.
sir.
See you.
Thank you.
Thank you.
Yeah. See you at Palkat, sir.
See you then. Thank you.
Actually, we are doing QIP program robotics, sir.
Oh, okay. So are you already here in Palakkad?
Yeah, we
sir,
were there from June 30th to July 11th, sir.
2 weeks. Again, will come in December 2 weeks.
Oh,
December
okay. So
also.
you guys are basically QIP scholars.
Yeah, we are faculty members.
Okay, so you'll be joining in the next semester, right? July.
Yeah, December we'll have 10 days.
And then when will you be
Mm,
joining as full-time scholars?
no,
No,
sir.
sir. We are
You won't be
working
joining.
professionals. We are professors in engineering colleges,
Okay.
and ACT provides a PG certification program, and we were selected in IT Palakkad under robotics.
Oh, okay. I thought you would be enrolling as PhD scholars. That's not the case, right?
No, no,
No.
no. We are
Okay.
already
Yeah.
working.
All right. Okay. Okay. But there are plenty of other faculties who are doing PhDs as under the QIP scheme. So I thought you guys would be something similar, right? So
Uh,
it's a course program, right? I suppose, right? Course
yes, sir.
certificates.
Yes.
Oh, okay. Okay. Oh, okay. Then we'll see once you are here. Then probably
Okay,
December.
sir.
Or something. Okay. Okay. Thank
Thank
you.
you.
Thank you. Thank you.